All right, here we go, advanced components. You're never gonna see these components. You're gonna buy a radio, and when it fails, you're gonna probably throw it away because you can't even find a way to fix it. But there's other parts too that you might see. Active components, practical circuits, and basic test equipment. That stuff you'll probably see. In fact, you will see most of it today. Active components, semiconductors. Semiconductor components are materials that do not conduct as well as conductors. Metal is better than insulators. So glass is an insulator, and copper is a really good conductor. And these are in the middle, and they kind of sort of let the power through, depending on how you. And so we can use the properties of these different metals to make semiconductors. They can modify the properties by adding controlled amounts of other materials called dopants. So doping is only bad in sports and electronics. We couldn't do anything without being, well, we couldn't do anything like we do today without being able to dope our semiconductor materials. So diodes and rectifiers, that little bottom there is the symbol. Let me look at the lights off so you can see that. The symbol there is for a diode. Which one's which? That is the symbol for diode. The cathode side generally has a stripe on it. And we have a P and an N. Can't remember what it is, but the P side, for some reason, has the negative sign, and the N side has the positive side. And they have holes. The stuff moves from one hole to the other, and how well it does that is what determines the characteristics of the transistor or the diode. So we have junction diodes. A PN junction like this, the diode allows current to flow only in one direction and blocks current flow in the other direction.
And yes, the arrow on there is correct. The current flow does go in the opposition to the arrow.
Yes. So when you hook up your car battery, you take off the neutral. Always take off the neutral last, right? Put it on last, or first, put it on last. That's because it doesn't actually flow from positive to negative, it flows from negative to positive. The diode allows current to flow in only one direction, from the N side to the P side. Junction diodes, the voltage is applied in the forward direction is called forward bias. So if you get a question about bias, forward or reverse bias. Forward direction is called forward bias. I believe that's the only question about it.
Probably.
Voltage applied in the reverse direction is called reverse bias. And the diode ratings, you must not be exceeded. Don't exceed the rating of it. I think we talked about it, but if you exceed it, you will oversaturate it. You can blow it up.
It'll just quit.
For good?
Sometimes it'll quit short, sometimes it'll quit open, but it will quit.
Yeah. All right, peak inverse voltage. You can't pass that up, exceed that. Maximum voltage in the reverse or non-conducting direction, reverse bias. So if there's voltage coming in this way and it's being used as a switch to say, no, it can't come this way, you can't overload it and blow it up. Maximum average forward current, the threshold, forward threshold voltage, so come in the right direction with the maximum voltage. Silicones, these two are on the test. Silicone, 0.0, 0.7, germanium, 0.3. Almost assured you're going to get one of those.
Yeah, that's in the general test.
Okay.
Wouldn't be surprised.
Yeah, it is.
Yeah.
Probably in the tech.
It is important. When you're in that program on the radio and you got your voltmeter on this and you're seeing a voltage you don't understand, look at the nature of the component. And so this would be on the test.
So, silicone 0.7, germanium 0.3. Gallium arsenide is another one, and gallium arsenide phosphide. And it's 1.2 to 1.5 volts approximately, but they're not on the test, so don't worry about it.
And you will rarely see them.
Are they expensive?
Yes.
That's why. Hands are cheap. Diodes are designed for low power signals called signal or switching diodes. So if they're designed for low power signals, they're signal or switching. If they're designed for high power circuits, they're called rectifiers. So rectifiers are diodes, they're just for more oomph. Maximum reverse voltage is as high as 1,000 volts on a rectifier. Maximum forward is as high as 200 amps of current.
That'll do it.
That works.
That's
That'll light you up.
housing bridge.
All right, diode types. You got a pin diode. Pin diode, there's a schematic diagram. So when you see these little drawings, that's what you would see on the schematic, and there are some schematic questions. Low forward voltage drop, and it's an RF switching and control type diode that we use it for. That's what the engineers and the makers do it for. We just push a button. Schottky diode. I thought that one was going to be yellow. The low junction capacitance allows operation of VHF and UHF frequencies. And you got a little backwards S. Kind of looks like an S, right? Just backwards. Dyslexic there. Has lower forward voltage drop. Varactor diodes, you got an anode and a cathode, and it's called a varicap. You see that right there? The cap is for what? Capacitor maybe? And that's a capacitor right there. So you got a diode and a capacitor. It's called a varicap. Can't remember what that one is.
That's another symbol for varicap.
It's the same thing?
Yes.
Okay. Okay, it operates with reverse bias. So it goes opposite direction of the others. I have no idea why you need that. There's guys that design radios. But look, nothing yellow. They're used for variable frequency oscillators and for FM modulators. Now, that one's yellow. Zener diode. Got those nice sharp angles. It's kind of like a backwards Z, isn't it? Or if you turn it to the correct, let's see, doesn't matter which way you turn.
And this guy is the basis for every voltage regulator in every radio.
So Zener diode operates with reverse bias at avalanche or breakdown voltage. So avalanche or breakdown voltage. You want to explain that?
Sure.
Because you're the tech.
The avalanche voltage is a peak voltage that it will sustain. So what you do is you apply voltage above the voltage that you want to maintain to that thing. And it only allows your reference voltage to go beyond it. So regardless of how that input voltage varies, that output voltage is going to remain constant, which is its job. That's what it does. So it operates right at the avalanche where it's just about to die.
They're designed to withstand avalanche current with the proper heat sink. So you got all that voltage coming in and it's holding it back and it's letting some through. There's going to be some heat. You got to let that heat get away. A lot of times anybody's looking at a computer and you see the little fins on standing up. That's a heat sink. Get the heat out of the processor.
And all that extra voltage will create heat, and that heat must go somewhere. So the dropping resistor that goes with these things oftentimes will have its own built-in heat sink.
Or it'll be bolted to the chassis or
Yeah, lots of opportunities.
And if you pull one off to replace it, which you probably never will, but if you pull one off and there's a little white goo underneath of it, make sure there's a little white goo under there as well, because that is what helps it get the heat out. That is to
It's a
make it.
silicone grease and it's designed to move heat. That's its only
Yeah.
function.
So, large change in the avalanche current results in a small change in voltage. Bipolar and field effect transistors. So I think we talked about those, FETs. Adding another layer to a diode creates a device capable of amplifying a signal. Why would we want to amplify a signal? Because your antenna is receiving millions or trillions of a volt coming in, and that ain't enough to drive the speaker for you to hear it, let alone all the electronics that have to process that before you can put out an audio signal. The first transistor was created at Bell Labs in 1947, and that is a recreation of it. They're ugly things. They're a lot smaller now. They're smaller they're probably smaller than one of the letters on the tag.
Yeah.
Oh, they are. We saw those.
Yeah, they are.
That little baggie, the sand in it, basically. Okay, bipolar transistors, a small current flowing between the base emitter junction controls a large amount of current flowing between the emitter and the collector. So it's like a valve. You can turn it on, you put a little more voltage, and it opens it up the valve, and a little less voltage, it brings it down. So when you're modulating the signal with your voice, it goes up and down, and it creates modulation that we can put on the signal. Bipolar transistors exhibit current gain. And remember we talked about gain? That's when we increase something, is gain. And there we go. So you got a base, collector, and emitter. You got a little arrow pointing out here, and this is your transistor. This is the circuit symbol. And that little circle there never points in. That's an NPN. That's how you tell it. Never points in. This one is a PNP. That little circle, that little arrow points in permanently. That's how you tell it. Okay, field effect transistor, or FET. So we got the source, the drain, and the gate. This is magnified about a bazillion times. And if you notice, the gate is on both sides here. And the source is the in, and the drain is the in over here, and this is going to be the B. Letters are a little small. The gate controls the channel current, gate voltage. The high input impedance on it, and enhancement mode, adding a positive charge to turn the gate on. So when you put positive to the gate, it turns it on and allows current to flow. Depletion mode is adding a negative charge to turn the gate off. So if we put it to the ground with negative, it turns it off. And there's how look at them. So we have an N channel. Ooh, that's hard to read.
Yeah.
So N channel, this side here is an N-type material, and then the P-type is up here. This one's the P-type down here, and the N-type up here in the purple. And then this is the gate. It's an oxide, and then this is the gate terminal. And so it is allowing the current to flow across to this point, depending upon the signal that comes into the gate. Metal oxide semiconductor field effect transistor, or MOSFET, which is on the test. The gate is separated from the channel with a thin insulating layer, which is that gate oxide there. Okay, bipolar and field effect transistors. High gain makes bipolar transistors and FETs useful as switches.
This might be really, really obvious, but the switching can happen very quickly.
In solid state,
Yeah,
incredibly fast.
yeah.
All right, low base current or low gate voltage puts a transistor into cutoff and allows little to no current to flow. Additional reduction of base current or gate voltage does not result in any further reduction in current flow. So whatever the low base current spec is, you get to that point, that's as much as you can control. Any lower, it doesn't do anything extra. High base current or high gate voltage puts a transistor into saturation or maximum current flow. Saturation is maximum current flow. Cutoff is little or no current flow. Additional increase in the base current or gate voltage does not result in any further increase in current flow. Operating points of the active region between cutoff and saturation. So you got the point where you can shut off the power, you got the point where it can't take any more. Of a bipolar transistor makes them useful as switches. So those two operating points, you can turn it off, turn it on, and you can do it super fast. The same is true of FETs. So that's the question there. Active region between cutoff and saturation of a bipolar transistor makes them useful as switches. Transistors come in a wide variety of packages, and there's a whole bunch of them.
And this is not all of them.
No.
Not even
Even close. Some high-power cases have collector or source directly connected to the base, so the metal is in enclosure.
Specifically, that circumstance is going to
Yeah.
apply to this guy and this guy.
Yep, you're going to see those bolted straight onto the chassis.
And occasionally that dude.
And sometimes you'll see this one sticking out. Gives them better heat transfer. That's why they do it. Must be insulated from the heat sink or chassis. Okay, so that's a vacuum tube. That's a very early one. It's the oldest amplification device, and it was invented by Lee DeForest in 1906. We didn't even start radio until the turn of the century. So, all right, triode. So, triode is 1, 2, 3, triode. It's the simplest tube capable of amplification. It's got 3 elements. It's got a cathode grid, also known just as the grid, and a plate, or the anode. Nothing yellow, though. The cathode is the source of the electrons. It's directly heated, indirectly heated, either way. At or near ground potential. It's got high current flowing through it. The control grid is yellow. It's a fine wire mesh. It controls the flow of electrons from the cathode to the plate. It's got a small negative voltage, low voltages, low current. That's the control grid. The plate, or the anode, collects electrons emitted by the cathode. It's got a high positive voltage, hundreds or thousands of volts. That's the one that'll bite you. All right, tetrode, 4 elements. This has got a cathode control grid and a screen grid. So this is the screen grid right here. It's also got a plate, and the screen grid is the primary purpose is to reduce grid to plate capacitance. So you're just trying to reduce the capacitance that's in there. So screen grid reduces grid to plate capacitance.
And that's the key phrase. It reduces grid to plate capacitance.
Right, screen grid reduces that. Medium to positive voltage, 150 to 200 volts, low current. So it'll bite you, but it won't bite you really bad. But low current could be enough to hurt you, because it doesn't say how much. Pentode. Pentode is 5. 1, 2, 3, 4, 5. 5 elements, a cathode, a control grid, a screen grid, a suppressor grid, and a plate. But there's nothing yellow on pentode. And the suppressor grid reduces the reflection or splashback of electrons from the plate to the screen grid. So they're coming this way, and it keeps them from splashing back this way, or they keeps them bouncing back. It's at or near cathode potential. It's often directly connected to the cathode. That's low current. And there's a whole bunch of different kinds. Some of these things we still use. The guys that have amplifiers, they're starting to get solid state amplifiers, but most amplifiers.
This guy right here, the 61462, is the basis for nearly every Kenwood hybrid transmitter.
Yes, ma'am.
I have a question. So, remember a long time ago, you guys said we don't use any of these anymore? They're all...
Oh, we still use them, but the new stuff doesn't have.
Oh, okay.
So, yeah.
That's why I was wondering.
And you, right, and you can still
It's
buy
still out there.
amplifiers.
It's still very viable.
Yeah, we call them boat anchors, because they're heavy.
Call them room heaters.
Room heaters, glow-in-the-dark guys.
Yeah.
But if you buy a non-solid state,
A little glow in the dark guy.
cheaper, and we're talking a couple $1,000s still, amplifier, it will have these.
I know you guys are rattling all these terms off, but I understand what you're saying. So what,
Slow it down.
is the vacuum tube only in an amplifier or
No.
transistor?
Oh,
No.
no.
They're like everywhere.
They used to be
They
in
used to.
everything.
Most everything
TVs,
today is going to use solid state exciters, solid state frequency control, solid state receiving systems. That's perfectly normal today, but it wasn't always that way. I've got some radios at home that would light the whole room.
So they went to transistors because they were smaller and they used less current. So you could make a transistor radio and carry it around in your pocket. Whereas before you had these big two portable radios running off a 45-volt battery with tubes in it.
so all the electronic stuff has changed.
And tubes are made from unobtainium now.
Unobtainium, yes,
Yeah.
that's a special material. Analog and digital integrated circuits, many transistors, diodes, and interconnections can be made on a single silicon wafer almost as easily as a single transistor, because robots. A device that combines several semiconductors and other components into one package is called an integrated circuit, or IC.
So what would an example of a device be?
There are no discrete components in this one. None at all.
So
There's
when
only
the screen-
one major chip and a screen. That one major chip has 1,000,000 different components doped into that chip. Some of them are capacitors, resistors, transistors, amplifiers, the oscillators, all of them are in that single chip. That's an integrated circuit. It integrates all of the components of a radio to create a radio into a single device.
or 3 or 4 devices
Yeah.
linked together. Digital integrated circuits, binary, base 2, number system used for digital processing. Binary is 1 or 2, 0 or 1, 0 or 1 is what we use. On or off. There's 2 choices, it's one or the other. Only digits are 0 and 1, on or off. Who here knows how to read binary? You and I are, of 4 of us. We're all extras too, aren't we? Okay, any number can be represented by a string of zeros and ones. That's called binary. 0 is 0, 0, 0. Why do we even go into that depth? 1 is 0, 0, 1, 2 is 0, 1, 0. Why would 2 be 10? 0, 1, 0 represents 2. 3 is 0, 1, 1. 4 is 100.
Now you can read binary.
Now you know the first 4 digits. They don't know all of them though. But you can represent any of the digits with binary code.
It's sequential.
0 and 1 can be easily represented by the off and on states of a transistor or similar device, because transistor turns things on and off, right? So if we line up a bunch of those in a correct sequence, we can make it say on, we can put out a binary string. Okay, complementary metal oxide semiconductor. Oh, that's a mouthful. Oh, we don't gotta call it CMOS. Replacing the TTL. It's not susceptible to noise. Ooh, that would be a good reason to have one. Yep. A CMOS. And digital logic, here we go. Okay, if you do not understand this, because it will be on your test, raise your hand or say something. Basic building block of digital circuit is called a gate. A not inverting gate and gate. So you have a gate, a not gate, and an and gate. And then an or.
What I want you to notice is there's 3 distinct characteristics here. This guy right here is the basic gate.
Okay, that's the gate.
Right. This is a not gate.
It's got a knot.
This is an or.
So this is a gate, because it's got the 0, the little circle there, or not, it's a not gate. This gives you a choice between A and B. Okay? And then there's the output, this is A and B, and the output. But this one is, this is an or, isn't it?
And.
That's an and this is, yeah, okay, and or.
That's an or on the right, yes.
So this one here, A and B are true, or false, depending on how it's done. If A and B are the same, you get output C. It opens up. If this one, if A or B, it goes out C. If I put the little circle not, then it's a not gate. So then it's A or B.
Both have to be off to create an output.
Right. A or B are on, it's a not going to let you through. Make sense? I think we're going to a little.
We do, we get into it a little deeper.
Okay, here we go.
Yeah.
So digital logic
Digital
gate.
logic
So
gate.
this is a basic gate. A and B. So you got A and B. So you got, if they're both, if A's off, B's off. If A's on, B's on. This is a not gate. If A is on, B is on. I'm sorry, if A is off, B is on. If A is on, B is off. Because it's a not. So there's not power there. So these are schematics. They show how things are connected, but they're not going to show you the power coming into that piece of that component. This is just switching. There's power coming in here, or there's not. And then whether or not it comes out or it opens. So it could be a ground over here. And then whether or not it allows it to come through. If A's on, B's on. If A's off, B's off. If A's on, B's on. This one is a not. So if A's off, it's the opposite. That's all. Just makes it switches it from the opposite of what's on A. The next one, one input element's non-inverting buffer, and inverting buffer or not gate. So this is non-inverting and that's inverting. It swaps the value. If it's on, it makes it off. If it's off, it makes it on. It inverts the signal coming in. This is an AND gate, looks like a D, and ends with a D. So a D is an AND. Okay, AND gate, if A is off and B is off, C is off, because you need A and B to get C. If A's on and B's off, A's off and B's on, we don't have both. So we got nothing. If A's on and B's off, we got nothing because they're not the same. If A and B are on, we get output on C. So if 3 are lined up, if A and B are the same, we get the same output that's coming in, going out C on an AND gate. On the NAND, not AND gate, we've got a little bit different. If A and B are on, or off, then C is on. If A is on and B is off, we got an on, because they're not both. So we get an output. A and, oh yeah. Okay.
Any of the single state input states will cause an output. If you do a dual.
Yeah.
You get no output.
It's not and,
Right.
either one.
Right.
So, okay, so then one of the A or B is on, C's on. A and B are both on, C's off, because it's both of them. So an AND gate, output is high only if all inputs are high. And a NAND gate, not AND, output is false only if all inputs are true. The only one that's yellow is the AND gate. Output high only if all inputs are high. Sequential logic. Check clock or synchronous logic. In a synchronous circuit, an electronic oscillator called a clock, or the clock generator, generates a sequence of repetitive pulses called the clock signal, which is distributed to all the memory elements in the circuit. And that's important because if they're not all at the right time, signals will be going down the wires at the wrong time, and then it'll all just not make sense and won't work. So everything's got to be spitting out what it wants to spit out at the appropriate time. Basic memory element, sequential logic is the flip-flop. The output of each flip-flop only changes when triggered by the clock pulse. So changes to the logic signals throughout the circuit all begin at the same time at regular intervals, synchronized by the clock. Flip-flop.
Yes, Leo.
A bistable, multi-vibrator, or latch. Several different types, such as D or T, gated and non-gated, clocked or non-clocked, can be used as a frequency divider. And I'm going real fast because you don't see the yellow. Can be used as a frequency counter. The current state is dependent on both the current inputs and the previous state. And it must include some form of memory. And there was nothing yellow, so don't worry about it. Just know that it's out there. Analog integrated circuits, operational amplifiers. Ooh. Circuit characteristics are totally controlled by external components. Amplifiers, active filters, adding signals. Didn't want to go that one. So an amplifier is providing gain. There's that gain word again. We use it a lot. Digital logic basics. So there's that little logic thing again. The D flip-flop is the most common. Okay. Computer RAM must be clocked. The T flip-flop toggles the state with each clock pulse. There's your logic again. Shift register, a clocked array of circuits. Okay, this one's on the test. A clocked array of circuits that passes data in steps along the array. And that's the little drawing of what it goes, boop, 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 and just pops right through each of those. And it keeps passing through. And the clock pulse allows it to step through it. It's called a shift register. Is a clocked array of circuits that passes data in steps along the array. So a clocked array of circuits is a shift register. Cascaded D flip-flops and converts serial data to parallel data. That can be useful because we've got all kinds of different connections now, and serial and parallel don't work together unless you have something to do.
When it comes to computing devices, does everybody understand the difference between series and parallel?
Say that again.
I see no hands, because I didn't.
Okay, so here's the deal. Serial devices, and we're talking about everything from USB clear back to 232 and 332, 422 devices, all send pulses down a single wire, one after the other after the other. Parallel devices use 8 wires. And they can send pulses down all 8 wires depending on what's going on. So your speed just went up astronomically in parallel. So that's what they're talking about here.
Parallel has 8 wires?
8, at least 8.
Converts parallel data to serial data on one of these shift registers, and serial to parallel. Digital counter, cascade with T flip-flops, do the same. Counts the number of input pulses. Number of states is 2, where N equals the number of stages. Nothing yellow.
And this you can forget. You will never see it.
Oh, but yes, you might. That question, because
Yes.
I don't think I've seen a test that didn't have that question.
And that's normal. We're at that basic binary there.
A 3-bit binary counter has 8 states. 3 bits is 8 states.
And does everybody understand how that happens?
Do you understand the
Okay.
answer to the question though? That's the only thing I care about on this part.
Seeing that question on that.
Okay, so here's the deal. A single counter has 2 states. The second counter has 2 more states. 2 times 2 is 4. That third counter out there doubles it again. So you've got 2 states, 4 states, 8 states with 3 counters.
So it's 3 to the third, or 2 to the third.
2 to the third.
By the time you get to 8 bits, it's 250.
Correct. You keep going out there, that 8 bits is that 256 characters is 8 registers on and off.
But the answer to the question that you're going to get is a 3-bit binary counter has 8 states, and that's the only part you have to remember. It's really cool.
That's the part that's on the test, but it's not where it comes from.
It's really cool to know all the in-depth stuff, but we don't want to just teach the test, but that's the part you have to remember to pass the test.
And if you let the smoke out of your radio, it quits working.
Oh, but they sell cans of magic smoke, put it back in. They literally sell cans of magic
Yes,
smoke.
they do.
Monolithic microwave integrated circuit, MMIC. VHF, UHF, and microwaves, typically 50 ohms. It's got a low noise figure, 3.5 dB to 6 dB. Okay, microstrip construction. So microstrip is just a little tiny bitty thing. The important part to you is that a MMIC is a monolithic microwave integrated circuit. Microprocessor and related components. That's a little thing that you might have seen in a computer if you ever opened one up. And then bunches of these little guys, look like little centipedes. Computer on a chip. Thousands of gates or transistors. They're all just, I don't know how they do it. It's electrons.
We're never going to know how they do it.
It's a super
It's a
expensive
computer
machine.
designed by a computer.
It's made in Germany, and there's like 2 or 3 of them in the world, and most of them are in Taiwan. Tens of thousands of transistors, tens of thousands
Yeah.
of transistors and diodes in these little guys. These are a microcontroller, microprocessor with interfaces to input and output devices, and it replaces complex digital circuitry. It's crazy small. And these things are in everything. You've probably got 1,000 of those, at least a couple of hundred of those in your car. Now, all those little legs have to be individually soldered on. Microprocessors and related components. So everybody know what that is? Or ever seen anything like that? Yeah, that's a RAM today.
What is it?
RAM, random access memory. That's the RAM in your computer. Looks probably like that.
Similar to that.
Close to.
Yeah, there's different configurations, but that's generally what it looks like. You can't just stick any old RAM into any old computer. You got to have RAM that's designed for that system. It is volatile. Anybody know what
Meaning?
volatile?
I'll say meaning what?
No, that's volatile organics.
All these simple.
It's Friday.
It's volatile. It's not volatile organics. Data is lost when it is powered on. Okay, that's volatile. So when you turn your computer off, anything stored in the RAM is lost. So if you've got your Word document or whatever you're working on and you didn't save it, it's in the RAM and you didn't save it, when you power off, you lost it. Okay, so there's another type there. That looks like one of those centipede things. That is read-only memory, or ROM. So it's programmed, it's got data in it, and you can read it. And it is not volatile, so when you power off, that data still stays in there. So this is how they program your emission systems on your car. This or this. The data is retained when it's powered off. And then the next one is an EEPROM. Programmable read-only memory, or PROM, as erasable programmable read-only memory is EEPROM. So this is when they got, you get a recall in your car, and so you got to come in and plug in a computer, and they go, okay, it's fixed. They reprogram the EEPROM. They generally it's called flashing it. So it's electrically programmable, erasable, read-only memory, or EEPROM. Nothing red, nothing yellow, but just stuff to know. Okay, interfaces. You got serial is 1 bit transferred at a time. So that's that single pulse. 2 impulses. RS-232 2, or COM ports, are commonly used to connect amateur transceivers to personal computers.
Bruce, take a break.
Serial interface and RS-232 COM. Right now, we use USB, Universal Serial Bus. That's replaced the RS-232. A lot faster, and they're standardized. So, interfaces, you have parallel interface, multiple bits transferred at a time, used for connections to mass storage devices, because you want to dump data quick. So, it's like parallel roads on a highway, you get more traffic through it. Integrated drive, ADV, and the small computer system interface. Are they using SCSI drives anymore?
No, SCSI went away.
Centronics parallel port,